talk a little bit about the different type of spectra that you can observe coming from an astronomical source. You might be familiar with these ideas if you had learned about Kirchhoff's laws for spectra before. And if not, that's not really the terminology that your textbook uses, so I won't refer to it that way. But we have three different types of spectra that can occur. I could see once light is split by a prism, I could see like a continuous rainbow of colors. That's called a continuous spectrum, or your textbook refers to that as a thermal spectrum. I could see that entire rainbow of colors with a few discrete colors that are missing. That is an absorption line spectrum. Or I could see nothing superimposed with a few discrete lines where there is light. So it would be no light, no light, no light, this color, no light, no light, color, no light, color, no light. That's called an emission line spectrum. So we're going to talk about how each of these spectra are generated. What are the conditions? So question 1, what type of spectrum is produced when light emitted directly from a hot, dense object passes through a prism? So we have hot, dense energy source, and that light is passing through a prism. That is the top case that gives us our continuous or thermal spectrum. Just a little bit of terminology. Make sure we have this connection. When we're talking about something that's dense, what does dense mean? That means opaque. Dense enough that you can't see through it. All right. What type of spectrum is produced when the light emitted directly from a hot, low-density cloud of gas passes through a prism? So a hot, low-density cloud, light from that is dispersed by a prism, and that gives me an emission line spectrum. And again, low density, low compared to what, or what does low density mean? It means that you can see through the cloud. The cloud is transparent. So instead of dense, we could talk about opaque. Instead of low density, we could talk about transparent. Describe in detail the source of light and the path the light must take to produce an absorption spectrum. Well, I get an absorption spectrum when I have my hot, opaque source of light. Light passes through that, from that source, through a cool, transparent or low density cloud, and then onto my prism where it's dispersed into the spectrum. So the path is from hot, dense energy source through a cool, low density cloud. And then to spectrometer to observe the spectrum. There are dark lines in the absorption line spectrum that represent missing light. What happened to this light that is missing in the absorption line spectrum? So this is the nice part of thinking through emission line and absorption lines. If I am looking through this cloud and I can see the opaque source of light behind it, I'll get an absorption line spectrum. But if I look off angle, I'm just looking at the cloud, then that's the same as this. I'm going to have an emission line spectrum. So those photons didn't go missing. They just went in a different direction. They're not along the line of sight from hot, dense energy source through cooler, low density cloud to detector. They were emitted in a different random direction. Is when the atoms that make up that cloud absorb a photon of light coming from the source, doesn't hold on to it forever, that energy is eventually going to be re-emitted, and it gets re-emitted in a random direction. All right. Stars like our sun have low density gaseous atmospheres, actually plasma, surrounding their hot, dense cores. If you were looking at the spectrum of light coming from the sun, or any star, emphasize that, or any star, which of the three types of spectrum would be observed? Well, I have a hot, opaque source of light, and between that hot, opaque source of light and me is going to be a cooler, transparent atmosphere. So every star, when you look at it, is going to give rise to an absorption line spectrum. There are things in the sky that you'll see as emission line spectrum. There are things that you could in principle see as just a continuous or a thermal spectrum. But for stars, we're going to see them always as absorption line spectrum, because they're always going to be hotter and more dense inside the star than outside the star. So you always have this cooler, lower density atmosphere plopped onto the star. If a star existed that was only a hot, dense core and did not have a low density atmosphere surrounding it, what kind of spectrum would you expect this particular star to give off? Then we would see just that continuous rainbow. So a continuous or thermal spectrum. All right, I have our two students again. Eventually we'll get to have three, but for now it's just been the two talking to each other. Two students are looking at a brightly lit full moon illuminated by reflected light from the sun. Consider the following discussion between the two students about what the spectrum of moonlight would look like. Student 1. I think moonlight is just reflected sunlight, so we will see the sun's absorption line spectrum. Student 2. I disagree. An absorption spectrum has to come from a hot, dense object. Since the moon is not a hot, dense object, it can't give off an absorption line spectrum. Do you agree or disagree with either or both of the students? Explain your reasoning. So student 1 is in pretty good shape on this one. And student 2 hasn't squared the circle on something that is sticking in their head. So the surface of the moon is not 5,800 Kelvin, so you're not going to expect it to give off thermal radiation like the surface of the sun does. If the moon were a thermal source of radiation, it would be far off into the infrared, because the surface of the moon is much cooler than the surface of the sun. And what student 2 is missing out on is that the moon is just reflecting sunlight. So student 1 is correct. You would see the sun's absorption line spectrum and that reflected sunlight. There are some modifications, so it's not just like a perfect mirror reflecting, but that's the right basic idea. Okay, last question. Imagine you're looking at two different spectra of the sun. Spectrum 1 is obtained using a telescope that is in high orbit far above the Earth's atmosphere. Spectrum 2 is obtained using a telescope located on the surface of Earth. Label each spectrum below as either spectrum 1 or spectrum 2. So if I look at spectrum 1, it's a absorption line spectrum. I've got 1, 2, 3, 4 lines. The first spectrum. And then second spectrum, I'm not calling it number 2 officially yet, is again an absorption line spectrum with 1, 2, 3, 4, 5, 6, 7 lines. Okay. So those absorption lines are coming from material that is transparent, that is interacting with the light, and it will absorb the colors of light that the atoms that make up the material can interact with. Okay? So by passing through more material, I have to be picking up more lines. And it had to start with fewer lines before it passed through the atmosphere. So the spectrum that is taken from high above Earth's atmosphere has got to be spectrum number 1, because it has fewer lines, and then spectrum number 2 is the light that's detected after it has passed through even more matter by passing through Earth's atmosphere.